In this video, we'll be talking about our results after conducting the experiment N3. In part 1 of the experiment, we're focusing on the energy calibration of gamma spectroscopy system. The objective of this experiment is to understand about the energy calibration technique and to understand how energy affects the channel of gamma radiation detection. The equipments and materials used are a high voltage supply unit, detector, sample which is placed inside the HPG detector, liquid nitrogen, and lastly, computer hardware and software. The experiment is done by opening the system program firstly. Secondly, the file gv-demo.spc was recalled and a buffer window will open. Next, the selection for energy is selected and destroy is clicked to remove any existing data. The channel 8226 was then picked as the peak, then energy was entered into the system. Lastly, the library list was used as a reference to identify calibration peak. Moving on to the task, this shows the table of energy and channel. This is the graph drawn of energy versus channel, and the relationship obtained is a directly proportional relationship. This is because higher gamma energy will produce a larger pulse, which as a result, a higher channel is produced. This is why the graph obtained will be getting a directly proportional graph. Next, the importance of energy calibration in HPGE detection system is that raw signals don't automatically give the exact energy of radiation. Therefore, calibration is needed so that the system can correctly translate the pulse into meaningful numbers to be recorded.
For part 2, efficiency calibration of gamma spectroscopy system.
For objective part 2, the first objective is to demo peak efficiency calibration of HPGE detection system. And objective number 2 is to study the relationship between the energy and peak efficiency of gamma radiation detection. For the procedure, the first one, we need to select calibrate and then efficiency, and then we need to destroy. And then we need to open efficiency calibration table and graph. Then we need to double click the 1332.5 keV peak of CO60, and then in the upper section of sidebar, click the calculate efficiency, and then enter the data and time, then tick the checkbox, and then we need to click calculate efficiency, then OK. And then we need to repeat this process for all other peak.
For part 3, we conducted the gamma spectroscopy counting and analysis for quantification of radioactivity levels. For part 3, we conducted the gamma spectroscopy counting and is to perform gamma radiation counting using high purity germanium, or for short, HPGE gamma detection, and also to calculate radioactivity concentration of thorium-232, uranium-238, and potassium-40 in the soil sample. For part 3, first we open the lead shielding, place the sample on top of the HPGE detector, and then close the shielding. Then we set up the gamma counting by inserting real and lifetime to be 3600 seconds. Then we fill in the mass of the sample as 717.00 gram. Then we ran the counting, and after 1 hour, we click stop to get the results, and then we click analyze tab, and select entire spectrum in memory to get data of net area under gamma peak. This is the results for part 3. For uranium-238, we measured the net area under the gamma peaks of its total nuclei, lead-214 and bismuth-214 as 11,343 and 8,229 respectively. For thorium-232, we measured the net area under the gamma peaks of its total nuclei, thallium-208 and actinium-228 as 3,636 and 2,943 respectively. For potassium-40, we measured the net area under its gamma peak as 221. For the task of part 3, we calculated that the source activity of uranium-238 is 298.6 becquerel per kilogram. For thorium-232, we calculate that its source activity is 115.9 becquerel per kilogram. And for potassium-40, we calculated that its source activity is 56.2 becquerel per kilogram. In part 1, energy calibration of HPGE gamma detection is important to maintain the excellent energy resolution of the HPGE gamma detection. The energy calibration curve obtained from the experiment show that the energy is directly proportional to the channel of gamma radiation detection. In part 2, efficiency calibration is important, as the wider the range of energies covered by the set of efficiency at several energies, the higher the number of radionuclides, Bose concentration can be established to measure the main natural gamma emitters. So we found this equation for the peak efficiency at the specific energy of gamma ray from the efficiency calibration curve. In part 3, by using this formula, we have calculated that the source activity of uranium-238, thorium-232, and potassium-40 in the soil sample used are 298.6 becquerel per kilogram, 115.9 becquerel per kilogram, and 56.2 becquerel per kilogram respectively. In conclusion, we have found that the energy of gamma radiation is directly proportional to channel of gamma radiation detection in the HPGE detection system. We also have found this equation from the experiment, which describes the relationship between the peak efficiency of gamma radiation detection and the energy of gamma radiation. The radioactivity concentration of uranium-238, thorium-232, and potassium-40 in the soil sample used are 298.6 becquerel per kilogram, 115.9 becquerel per kilogram, and 56.2 becquerel per kilogram respectively.